Warning, do not copy. Our programs are covered by registered U.S. copyrights. They may not be duplicated or copied. Willful infringement constitutes a felony punishable by fine and imprisonment. Civil remedies include statutory damages of up to $50,000 per offense, plus plaintiff's attorney's fees.
Semiconductors Explained. Part 1. Basic Theory.
Semiconductor technology has been one of the fastest growing areas of electronics within the last few decades. Advances made in this area have led to the development of diodes, transistors, and integrated circuits, and has made possible the incredible reduction in size of electronic equipment.
Computer circuits, which once filled a room when built with discrete components, can now fit in the palm of your hand on a single semiconductor integrated circuit, or IC. In this series, the most basic semiconductor device, the diode, will be thoroughly examined. Several special-purpose diode devices, including the Zener diode, will be presented. Finally, the semiconductor characteristics of transistors will be explained, and integrated circuits will be introduced.
In order to fully understand the operation of semiconductor devices, it's necessary to know the theory upon which their construction and operation are based. Let's begin this first part by looking at some atomic theory.
From your study of electronics, you know that a conductor is a material that easily permits the flow of electron current. Copper is an excellent conductor of electricity. This is because of its atomic structure. A copper atom has 29 electrons circling its nucleus, 2 in the innermost shell, 8 in the second shell, 18 in the third shell, and just 1 in the outermost or valence shell. All of the 29 electrons carry a negative charge. These are offset by an equal number of positive charges carried by protons in the nucleus. This results in an electrically neutral state.
There's a shorthand method of visualizing an atom. Since the outer or valence electrons are the important ones to consider in a study of electronics, the copper atom can be more simply drawn this way. Notice the nucleus with its 29 protons and the valence shell with its 1 electron. Now let's see why the valence shell is so important in determining which elements are conductors, which are insulators, and which are semiconductors. Here's an important valence shell principle.
The fewer electrons in the valence shell, the more loosely bound they will be. Remember, copper has just 1 electron in its valence shell. It takes very little energy to dislodge it. With the aid of some external force, such as a voltage source, the direction in which these dislodged or free electrons move can be controlled. This is what makes copper such a good conductor of electric current.
Here's a second important valence shell principle. The more electrons found in the valence shell, the more tightly bound they will be to the nucleus. A full valence band makes the element a good insulator. The best insulators have 8 electrons, which is the maximum number that can reside in the valence shell. This type of atom is very stable. It would take an enormous amount of energy to dislodge these rigidly held electrons.
Insulating materials, such as plastic, are used to prevent electron current from flowing outside the desired path.
Since the human body is able to conduct electric current, you must make sure that you are properly insulated from any conductive paths. Here are some personal precautions.
For your own safety, remove any jewelry you may be wearing on your hands. Jewelry is a good conductor of electricity. Since you'll be working on electronic equipment, You want to minimize the risk of any potential shock. In addition, make sure to remove all other jewelry, such as necklaces. Although earrings like this don't dangle, remove them anyway.
Always wear some form of eye protection.
There is no special clothing requirement for electronics technicians other than common sense. No loose clothing that can get caught in the moving parts of an electromechanical device, for example. Here are some precautions for equipment. Never use equipment with damaged cords. Only use tools that are properly insulated. Consider all wires hot. Use an isolation transformer.
Remember, safety always comes first. The atomic structure of both conductors and insulators has been shown. Now, let's see what a semiconductor looks like at the atomic level.
Semiconductors have 4 electrons in their valence shell, which is too many to be a good conductor and too few to be a good insulator. Having 4 valence electrons means that semiconductors are somewhat unstable. They can become stabilized by getting additional electrons to fill up the outer shell. But since the 4 valence electrons in any one atom are bound as tightly to their nucleus as the 4 in any other atom, one can't pull electrons away from another. Instead, 2 nearby atoms will share their outer electrons. This sharing of valence electrons is known as covalent bonding.
2 types of semiconductor material that have been used to make electronic components are germanium and silicon. Silicon's operating characteristics are more stable over a wider range of temperatures, so it's more widely used than germanium. Because of this, we'll focus primarily on silicon in this series. Let's see how silicon atoms form covalent bonds. Notice that this central silicon atom, labeled Si, shares its 4 valence electrons with those of 4 neighboring silicon atoms, resulting in a complete valence shell, which is very stable. This orderly pattern into which the silicon atoms have become arranged is called a crystal. Although quite stable, these covalent bonds can still be broken if some external force is applied.
One such force is thermal or heat energy. As the ambient or air temperature around a silicon crystal increases, its electrical resistance decreases. Decreasing resistance means increasing conductivity. Let's see what this means at the atomic level. At a temperature of absolute zero, the covalent bonds between silicon atoms are very strong. The electrons cannot move through the crystal. But as ambient temperature increases, the heat energy absorbed by some of the valence electrons can cause one of them to be lifted out of its orbit. Once dislodged, the electron no longer belongs to its original silicon atom and is virtually free to move from one atom to another. For this reason, these dislodged electrons are more commonly known as free electrons. After the electron leaves, a space is left behind in the valence shell. This space is called a hole, and it serves an important role in semiconductor devices.
Let's visualize this in another way, using something called energy bands.
A silicon atom contains 14 electrons, 4 of them in its valence shell. But remember, we're examining at the atomic level. In even a very small piece of pure silicon, there are millions of individual silicon atoms. While studying semiconductor theory, it can be helpful to group together all of the electrons that exist in the first shell of all the atoms in a piece of pure silicon and indicate them like this. This energy band represents electrons in the first shell. They can be grouped together this way because the attraction between the nucleus and the first shell electrons of all silicon atoms is identical.
Similarly, all second shell electrons also exist at the same energy level and can be designated with a higher energy band.
Likewise, all valence electrons, which are at an even higher energy level, are grouped together into what's called the valence band.
There is actually another energy band above this one, known as the conduction band. At a temperature of absolute zero, the conduction band is empty.
Remember, however, that as the ambient temperature increases, some valence electrons are lifted into a higher orbit where they become free electrons. These free electrons, whose attraction to the nucleus of their atoms is negligible, can be grouped into the conduction band. Again, notice the holes left in the valence band. These holes are important because they will tend to draw electrons into them. Because they have an attractive force upon the negatively charged electrons, the holes can be thought of as having positive charges. They're not really positively charged particles like protons, but they behave like them.
Let's look at the valence band more closely to see what happens to a hole as it draws an electron into it. Notice that as an electron moves to fill the hole, another hole appears. As the electrons move to the right, the holes seem to move to the left. In fact, electron movement and hole movement always occur in opposite directions. This movement of holes within the valence band of a silicon crystal is known as hole flow. It's one type of flow found within a semiconductor.
Another type is electron flow. This is created by the movement of electrons through the conduction band. Remember that thermal energy alone can cause some valence electrons to be lifted into the conduction band where they move through the semiconductor as free electrons.
Remember also that for each free electron in the conduction band, there is a corresponding hole in the valence band created by each departing electron. The higher the ambient temperature, the more free electrons and holes there will be. Occasionally, a free electron in the conduction band may overlap one of the holes in the valence shell of an atom and be drawn into the hole. The action of a free electron moving into a hole is called recombination. When recombination occurs, the hole in the valence band disappears.
Hole flow, electron flow, and recombination occur purely at random within a semiconductor as a result of thermal energy. There's no set pattern or direction to the movement.
But by subjecting the semiconductor to an electromotive force, the direction of current through it can be controlled.
However, even at room temperature, there isn't enough current created by thermal energy to be useful. In addition, it wouldn't be desirable to allow temperature to determine how much or how little current flows. You wouldn't want your radio to operate any less reliably at 85 degrees than it does at 65 or 70 degrees.
Since semiconductor material in its pure form is of little use in the conduction of current, another strategy has been developed to take advantage of its unique properties.
By adding other materials to the pure semiconductor, its conductive properties can be greatly enhanced. This process is known as doping. Doping can either increase the number of free electrons or the number of holes, depending on what type of material is used. Whereas a pure semiconductor is known as an intrinsic semiconductor, after doping, it's referred to as an extrinsic semiconductor. It's good to know these terms because you'll come across them in your work with semiconductors.
A doped or extrinsic semiconductor can be one of two types, N-type or P-type. An N-type semiconductor is produced by adding an element whose atoms have 5 valence electrons. These are known as pentavalent atoms. The prefix penta means 5. Arsenic, labeled As, is a common pentavalent element used for doping. An N-type semiconductor is formed when silicon is combined with arsenic. The pentavalent atom forms covalent bonds with 4 neighboring silicon atoms. The 5th electron of the original arsenic atom is released as a free electron. Remember, since the valence shell of any atom can hold no more than 8 electrons, the extra one travels in the conduction band as a free electron. As a result of the doping process, many new free electrons are produced. Since each pentavalent atom that is added contributes an electron, the total number of free electrons is determined by the amount of pentavalent material added. Notice that there are still a few electron-hole pairs generated by thermal energy, but these are far fewer in number than than the free electrons produced by doping. Since there are many more free electrons than holes in an N-type semiconductor, the electrons are the majority current carriers, and the holes are the minority carriers.
A P-type semiconductor, on the other hand, is formed by doping a pure crystal to make more holes. This is done by using trivalent atoms. As the prefix implies, these atoms have 3 valence electrons. This silicon wafer has been doped with boron, a trivalent element. Gallium, labeled Ga, is another common trivalent element used for doping. When combined with silicon, each trivalent atom will form covalent bonds with 4 neighboring silicon atoms. But since each brought with it only 3 valence electrons, there will only be 7 in the valence orbit at the center. In other words, 1 hole appears in the valence shell of each trivalent atom. Again, by controlling the amount of trivalent element added, the number of holes in the doped crystal can be controlled. Notice again that there are still a few electron-hole pairs generated by thermal energy, but these are far fewer in number than the holes produced by doping. Since the holes of a P-type semiconductor far outnumber the free electrons, they are the majority current carriers, whereas the free electrons in this case are the minority carriers.
Now let's see what happens when an extrinsic or doped semiconductor is subjected to an electromotive force.
In the following graphics, minus signs will be used to denote the negative charge carried by each electron, and plus signs will be used to indicate the positive attractive force carried by each hole. In this N-type semiconductor, electrons from the voltage source enter on the right, propelling similarly charged free electrons within the crystal toward the left, where they leave the semiconductor and are drawn back toward the positive side of the voltage source. A few of the free electrons will not make it through the crystal because they'll fall into valence band holes. Remember that holes move in a direction opposite to that of the electron flow, and that they are the minority carriers in N-type semiconductors.
In P-type semiconductors, the valence band holes that are produced by the doping process far outnumber the few free electrons that are the result of thermal energy. As the electrons from the voltage source enter the semiconductor on the right, they fall into the valence band holes and move through the crystal from hole to hole as valence band electrons. As they exit the crystal on the left, they again become free electrons and return to the voltage source. Once again, the holes appear to move from left to right as they are attracted by the negatively charged electrons entering the semiconductor.
Although we've examined the current flow through extrinsic semiconductors, there is little advantage to using N-type and P-type crystals separately because they simply behave like resistors.
The truly unique properties of a semiconductor crystal can be exploited only when the crystal is doped so that half the crystal is P material and the other half is N material. The point at which the two different materials meet is called the PN junction. Although here it's graphically represented as a line, it's not really a mechanical joint. The crystalline structure is actually continuous. There's another name for this PN semiconductor. It's more popularly known as a junction diode, symbolized this way. Let's see how the diode symbol correlates with the graphic of the PN semiconductor that you've seen. One side of the diode is called the anode and is composed of P-type material. The other side is called the cathode and is composed of N-type material.
When P-type and N-type materials are combined in this way, the semiconductor crystal exhibits electrical properties that are amazing. Let's stop here and review what you've been shown.
In this part, you've been introduced to the basic theory behind semiconductors.
At the atomic level, you saw that a semiconductor has 4 valence electrons, which creates a tendency to form covalent bonds where electrons are shared.
You saw how electrons flow as compared with hole flow.
Finally, you are presented with the combination of P and N material, which forms a junction diode.
In the next part, you'll see how this basic semiconductor theory applies to junction diodes when forward and reverse biased.